welcome everybody. Thank you for being here with us today. This is the first time that we are actually doing this event, that is SISSA Women in Mathematics. Today is a special day because it's the birthday of Mariam Mizakani, and it's the World Day of Women in Mathematics, and SISSA this year decided to, let's say, organize this event. And for me, it's a great honor being part of the organization of this event. For the one who don't know me, I'm Maria, and I am a last year PhD student. But the ones who know me basically know how this theme is really, dear to me. So I'm really happy of being involved in this event. So the event actually consists in two seminars, one given by Chiara Rigoni and the other one given by Ada Boralevi. And both the speakers were somehow involved in SISSA community, and they maybe will share their experience in SISSA besides their research teams, maybe with us later. So now I will leave the floor to Professor Grava in order to introduce the first speaker, Chiara. And if you want, Chiara, you can share your screen. Meanwhile, thank you.
Okay, so thank you, Maria. And so we welcome I welcome everybody, and particularly welcome the first speaker, which is Chiara Rigoni, which is in University of Bonn. And so, well, the title is on the board. So the screen is yours, Chiara, and welcome.
Thank you. Thank you very much for the organizers for the opportunity to present my work in this very nice event. And also thanks for the opportunity to be at least virtually in SISSA, where I spent 4 beautiful years. So the topic of my research is focused on the study of analytic and geometric properties of metric measure spaces bound on the Ricci curvature. So first of all, let's start introducing this class of spaces. Our starting point is the following theorem by Gromov, which says that
Sorry, Chiara, I don't know if I'm having a problem, but I can hardly hear you. I don't know if I'm the only one.
No, the same for me.
But before it was working.
Seems like you are touching the microphone or something. There is a strange echo, like.
Yeah, it went. You touched something because
at the beginning it was fine, and then somehow it.
Okay, I try not to touch the keyboard.
Yeah, no, now it's much better, Chiara.
Okay, perfect. So we were saying that our starting point is this theorem by Gromov, which says that the set of all compact and dimensional smooth Riemannian manifolds bound from below on the sectional or Ricci curvature and bound from above on the diameter is relatively compact in a suitable topology. So in the case in which we consider the case of the sectional curvature, the topology, the right topology to focus on is the one given by the Gromov-Hausdorff distance, which measure how far are two manifolds from being isometrics. What we find as limits of these sequences converging the Gromov-Hausdorff distance are the so-called Alexandrov spaces, which are no smooth spaces in which a lower bound on the sectional curvature can be introduced. So let's see how we can define these Alexandrov spaces, first of all, just to have an idea on how we proceed, because the philosophy is more or less the same as the one of behind the notion of CD spaces. What because the point is that here what we find as limits of these sequences of Riemannian manifolds are in general non-smooth spaces. So in these non-smooth spaces, we don't have anymore a Riemannian curvature tensor from which we can compute and derive some quantities. But we have to follow a synthetic approach. So focus our study on some geometric properties that these bounds on the curvature are implying on the manifold, or more in general on the space. So in the case in which we are considering the sectional curvature, these synthetic notion come from this Toponogov triangular comparison theorem, which says that if we have a smooth Riemannian manifold, it is equivalent to have a bound from below on the sectional curvature by some constant to the fact that geodesic triangles in the manifold are fatter than triangles in some reference space, in some model space. So let's see what it means to be fatter for a triangle. So first of all, let's start noticing that when this k is greater than 0, the model space to consider is the one with the constant curvature, which is the two-dimensional sphere with radius 1 over square root of k. In the case in which k is equal to 0, the model space we consider is the Euclidean plane. And in the case in which k is negative, we consider the hyperbolic plane with the parameter 1 over square root of minus k. So now how we proceed? We take 3 points on our manifold, and we join them, so 3 distinct points, and we join them with some geodesic, with the geodesic connecting these 2 points. Then we take other 3 points in the model space in such a way that these lengths are the same, so the 2 triangles are comparable. What we do now is to fix a vertex that we call Z, and we take the opposite edge, which is this one, and we take the geodesic, which is in the opposite edge, so we can parameterize it with a parameter, the time parameter. Now we take the geodesic, join the vertex with any of these middle points between gamma 0 and gamma 1, so this gamma t, and we see the distance between this z and this gamma t. Then we compare it with the same constructor in our model space. And if this length is greater than this one, we say that this triangle is fatter than the one in the model space. So as we can see, here we have a constructor on the bound on the sectional curvature. At this point, it does not depend anymore on the Riemannian curvature tensor. The only concept that we need is the one of length. So we can take this characterization and turn it into a definition. And we say that a locally compact complete length space is an Alexandrov space if we can find a comparison that
Yes, so sorry, Chiara, to interrupt. We don't hear. I don't hear anything now.
I don't know what is, because I was just touching the mouse pad.
Okay, yeah.
The first time, okay. I try not to touch the mouse pad. Okay. So the concept of our Alexandrov spaces is introduced by this comparison of triangles. Now we follow more or less the same, in a sense, as we were saying, we follow the same philosophy in order to give the concept of CD spaces. So in order to treat the case of the Ricci curve, of a lower bound on the Ricci curvature. So in this case, the measure plays a fundamental role, as we can expect, because we know that once we have we know that in general, in the case of manifolds, the Ricci curvature is something that controls the evolution of the volume along geodesics. So the measure plays a fundamental role. And so what the right topology to consider is the one given by the measure Gromov-Hausdorff distance. So in this case also the distance between, somehow the distance between measure is important. And what we find at the limit are no more just metric spaces, but are metric measure spaces, satisfying this CD condition. Let's see how we introduce, so what is the synthetic notion behind. This is given by the, and first of all, we have to introduce the background in order to give this synthetic notion. And this is given by we have to introduce some notion in the optimal transport theory. So we start with a complete and separable metric space. And we introduce P2, which is the set of probability measures which have finite second moment, meaning that this integral is finite for any fixed point in the space. Now, for any couple of measures in P2, we can introduce the following Wasserstein distance, which is formulated in terms of, again, of an integral of the distance squared with respect to this measure gamma, where this gamma is a measure a probability measure in x times x, so in the space-time itself, and such that the projection in the first marginal gives us our measure mu, and the projection in the second marginal gives us our measure mu. Very well, so it turns out, and we take the infimum among all these families of gamma. Now, it turns out that actually this Wasserstein distance is actually a distance in P2, and the metric space, which is resulting, that we call Wasserstein space, is actually complete and separable. We can speak about geodesics in this setting, and it's so a Wasserstein geodesic is a curve in P2 such that we can evaluate the distance between two intermediate points, so the measure at time s and the measure at time t, as the difference between the two times and the measure of the starting and final point of the curve. It turns out in particular that once our complete and separable metric space is also geodesic, also the Wasserstein space is geodesic, which is a very nice property because now we can work speaking about geodesics, so in Wasserstein space. This is in the setting of metric spaces. So once we endow this complete and separable metric space with a radon measure, we can then introduce also the following functional, which is the entropy functional and depends on this fixed measure m. So we define it in P2. And we define for mu, which for the set of measure mu, which are absolutely continuous with our reference measure m, in terms of the density of this measure mu with respect to m. So in the case in which so it's absolutely continuous, we have this integral, define the entropy. Otherwise, we set it to be plus infinity. A property of this entropy that we are interested on studying is the so-called K-convexity in the Wasserstein space. So we say that the entropy is K-convex in the Wasserstein space if for any couple of measures which have finite entropy, there exists a Wasserstein geodesic such that along the geodesic, this inequality holds true. So this allows us to give the synthetic notion behind the CD condition, which is this theorem by Sturm and Forrenesse, which says that if we have a smooth Riemannian manifold, it is equivalent to have a bound from below on the Ricci curvature to the fact that the entropy is K-convex in the Wasserstein space. Indeed, we have that if we have a smooth Riemannian manifold, we have a Riemannian metric tensor. From this, we can derive a way to measure a distance between points, and we have also a volume measure. So we can introduce the concept of entropy, and moreover, we can also introduce the Wasserstein space. So this is important because we have a characterization of a lower bound on the Ricci curvature in terms of how much is rarefied the entropy in the intermediate points of Wasserstein geodesics. Moreover, if we have, so this theorem is, depends just on the fact that we have a Wasserstein space that, as we said, we can construct it once we have a complete and separable metric space. And we have the fact that we have a measure. So we can take this characterization and turn it into a definition, which was first introduced by Lotten-Villani and Sturm independently. And it's, so once we have a metric measure space, we say that it has a lower bound on the Ricci curvature by some constant k if the relative entropy is k convex in the Wasserstein space. So in particular, here in short, we call it CD K infinity space, where CD means curvature dimension. And the fact that here there is an infinity means that by now we have not introduced a notion of an upper bound on the dimension. In order to do it, we have to change a bit our entropy that we were considering. So we take a parameter n, which is greater or equal than 1, and we can define the Rényi entropy functional following the same philosophy. So it's again something which is defined in P2, and it's defined for absolutely continuous probability measure with respect to our reference measure n. This is the expression that we have, and plus infinity for all the other measures. And in particular, we notice that this functional is convex with respect to our reference measure n. So before, for the entropy functional, we were speaking about K convexity. Here we have also the parameter n, so also this convexity has to be modified according to the fact that we have a bound on the dimension. And the right notion to consider is the one of Kn convexity introduced by Sturm in 2006. So we say that a metric measure space satisfies the CD Kn condition. Again, if for each pair of probability measurements in P2, there exists a geodesic such that this inequality now is satisfied. And this inequality, so it's formulated using these distortion coefficients. And I just want to underline that actually when k is equal to 0, this coefficient is equal to 1 minus t, this other coefficient is equal to t. And what we find is exactly the standard notion of convexity for the Rényi entropy functional. This class of spaces is quite nice because we have we have the compatibility with the Riemannian case. So if we have a Riemannian manifold which has a bound from below on the Ricci curvature and a bound from above on the dimension, this is a CD Kn space. Moreover, we have the stability with respect to measure Gromov-Hausdorff convergence, that it was the thing that we were hoping at the beginning with, in a sense, it's something that we wanted from the Gromov's theorem. And yeah, and let's underline that once we have a CD Kn space with n finite, this is also a CD K infinity space. So in a sense, there is this monotonicity in the dimension. So another important observation is the fact that actually Finsler structures are included in this setting of CD spaces. What does it mean, Finsler structure for a manifold? It means that if we, intuitively, if we take a manifold and we look at the tangent space, what we have in the tangent space is a scalar product. And if this scalar product comes from what we have in the tangent space is a norm. If this norm comes from a scalar product, this is a Riemannian manifold. Otherwise, in general, is a Finsler manifold. So we have that Finsler structures are are actually included in this set of CD spaces. And this can be seen if we take the n-dimensional Euclidean space and keep with any norm and the Lebesgue measure. This is a CD 0n space. The reason why we are a little bit not so happy about not so happy, we are like we want to restrict to Riemannian-like structures, is the fact that actually the behavior of Finsler and Riemannian manifolds is quite different, and this can be seen both from the point of view of the analysis and from the point of view of the geometry. For example, some difference is the fact that in Finsler manifolds, we cannot identify tangent and cotangent space. And this is more an analytic property, while in the case of Riemannian manifolds, we can do it. And another point is that many rigidity results are not valid in the case of Finsler structures, but they are valid in the case of Riemannian manifolds. So we would like, if we, in a sense, keeping in mind that we would like to find some geometric property of these CD spaces, we have to find a way to distinguish these two kind of behavior. This the key point in in finding a discriminant between the two structures is the study of the Sobolev space. So I just introduced the ideas behind one of the possible constructor of the Sobolev space. And so our starting point is again the one of Riemannian manifolds. And we know that in this setting, we have the possibility, it's quite natural to introduce this energy, which is defined so in terms of this gradient of smooth functions. This the domain of this energy is called the Sobolev space on the Riemannian manifold. And now what we would like is to mimic a little bit the constructions of the Riemannian manifolds. But the problem is that here we have a non-smooth structure. So in particular, we don't have at our disposal a way to speak about gradient of functions. So what was the idea behind the Cheeger and the definition of the Cheeger energy is exactly this thing. So we don't have the gradient, we take a relaxation of it. So this was introduced by Cheeger and then by Ambrosio, Gigli and Savary. And so we said that we take a relaxation. So we take any function in L2, and we take a sequence of Lipschitz functions with bounded support that are converging to our F in L2. What we take is then the limit of this integral, which involves the metric slope of these of the functions of these Lipschitz functions in the sequence, and then we take the inf among all the sequence which are approximating in L2 our starting function. Very well, so this defines an energy that we said that it's called Cheeger energy, and it can be proved that it is a convex and lower semi-continuous function, and that the domain of this Cheeger energy is actually dense in L2. And this is important because it allows us to see that if we have a function which is in the domain of the Cheeger energy, then this collection of L2 functions for which we can find a sequence of Lipschitz function with bounded support that are approximating our starting F, and such that the metric slopes are weakly, are converging it to G weakly in L2. This actually admits a unique element of minimal norm in L2, and this is called the minimal weak upper gradient. This is important because once we have the minimal weak upper gradient, we have a way to represent the Cheeger function, the Cheeger energy, mimic what is done in the case of what is true in the case of Riemannian manifolds. So here, let's underline that we don't have actually a gradient, but we have an L2 function, And here we are taking the integral of this L2 function squared with respect to our reference measure. The domain of this Cheeger energy now is the so-called Sobolev space. Very well. So now we can. This was the notion that allows us to give a difference between Finsler and Riemannian structures, and so this is a key notion. And it was so the definition given by Gilli in 2015 is the one of infinitesimal Hilbertian spaces that are metric measure spaces for which the Sobolev space is that in general is just a Banach space. In this case is also Hilbert. And this actually is really the discriminant also in the setting of Riemannian manifolds. So if we have a manifold in general, we look at the Sobolev space. If it is an Hilbert space, then our metric measure, our manifold is actually Riemannian and not just Finsler. So this at the level of the energy means that the Cheeger energy is actually a quadratic form. Now we are ready to give the definition of RCD Kn spaces given by Ambrosio Gilli Savare in 2011, which is the one of, so RCD means Riemannian curvature dimension condition. And so we say that a metric measure space satisfies this RCD condition if it is a CD Kn space and the Sobolev space is actually Hilbert. So it's an infinitesimal Hilbertian space. What is important now is the fact that we are able to rule out all the Finsler-like structures from the class of CDKN spaces and to restrict our study just to the cases in which our metric measure space has a behavior which is similar to the Riemannian one. And this is important once we would like to, we want to prove some rigidity results. So in the last years, many results have been proved. And actually, this is really just a short selection. The reason why I chose these four results is the fact that the first two are more geometric. So they rely on the existence of some nice function on the space, and from the existence of this function, we can deduce some geometric properties of the space itself. In particular, the splitting theorem, which was the one that we were mentioning before, that it also in Riemannian manifold but not in Finsler structures, says us that if we have an RCD 0n space and we can find a line inside, then we can write this metric measure space as a product of R times our RCD 0n-1 space. As for the second two results that I mentioned here, they are more a little bit analytic in the sense that the rigidity on the space is proven once we have some decays of the equality in some functional inequality. Very well. So in this, moreover, in this class of RCD spaces, not just a first-order differential structure can be built, but also a second-order differential structure. And this was the key point in the proof of the, or better, also in the formulation of the main result proven in my PhD thesis, so with Professor Nicola Gilli. And once we have, which is a generalization of Bochner, of a theorem by Bochner, and says that if we have a metric measure space, which is an RCD 0n space, then the dimension of the first cohomology group in the de Rham cohomology is at most equal to n. And the case of the equality can appear if and only if our metric measure structure is isomorphic to the n-dimensional flat torus. So this is what I wanted to present for the let's say classical theory of a curvature dimension condition. And now I would like to present some results proven during my postdoc here in Bonn. And so first of all, I would like to, if there are some questions, I don't know if, I saw that probably there is something in the chat, but probably it's because of the sound.
If you have questions, you can unmute yourself or write them into the chat.
Otherwise, let me go on and
Yes, exactly.
don't feel pressed.
I think that you can.
Okay. So in the second part of my talk, I would like to present some generalization of this curvature dimension condition. And first of all, I would like to present the case in which the dimension is actually negative. So let's start with the definition of this, and then let's see why it's important. So as we were saying, the class of CDKN spaces was introducing by defining a suitable entropy functional, and then the key point in the definition is this Kn convexity of this functional. What we so in the case in which we want to generalize to the case in which n is negative, first of all, we have to define again a suitable generalization of the Rényi entropy functional, which is actually, it takes the same form, but why I would like to underline that here the minus sign is dropped, because once n is less than 0, this functional is already convex with respect to m without the minus sign. So now, second step, which was done by Hota in 2015, is to generalize also the Kn convexity to the case of negative n. Again, it takes actually the same expression, and also in this case, the minus sign here is dropped. So again, when k is equal to 0, we find the standard convexity of our entropy functional. So, as we were saying before, now we see some motivation, because if we think about the dimension as an upper bound on the topological dimension, considering the negative values of the parameter is quite a strange thing, right? But actually, the motivation goes back to the setting of weighted Riemannian manifolds. So let's take a manifold, and let's take a Riemannian manifold with a volume form, and let's take as measure, reference measure, this omega, which is a weight of this weighted volume measure, and the weight is given by this function psi. So once we have this weighted measure, also the Ricci curvature tensor is changed according to this to the fact that we have a weight, and in particular the Hessian of this psi that we consider smooth. So the Hessian of psi is appearing, and also here we have the term involving the gradient of this psi. This in particular is formulated in terms of this parameter n, which in general, so in the standard theory, is taken to be greater or equal than, or better, greater or equal than the topological dimension of the manifold. The case in which n, capital N, is equal to the dimension is the case in which we have no weight, actually. So in the standard theory is, as we are saying, it's positive. But it turns out that in this setting of weighted Riemannian manifolds, there is this n relative entropy, which is denoted by HM, which is an important object because, for example, in a series of papers, it was proven that the gradient flow of this n relative entropy produced a solution to the porous medium equation when m is greater than 1, and to the fast diffusion equation when m is less than 1. So it has really an analytic mini. And it was proven that actually by Hotta and Takatsu, that actually the fact that the M relative entropy is K-convex in the Wasserstein space is strictly related to the fact that our Ricci Ricci curvature tensor is non-negative. And this n is depending on the parameter m that can be anywhere in R except from 1. In particular, when m is greater than 1, here we have n, which is negative. So the reason why the negative dimension is appearing is exactly in this setting of weighted Ricci curvature tensor. Many examples of these weighted Riemannian manifolds with negative dimension have been found out. And for example, in the Euclidean setting, if we take the n-dimensional Euclidean space with the Euclidean distance and these families of probability measures, which are called heavily tailed measures, it can be proved that this is a CD0 minus alpha space, where alpha is any positive parameter. Here, this C is just a renormalization in order to have a probability measure. And actually, this family of heavily tailed measures was generalized by Millman in the case of the sphere. And he proved that actually also, if we have this family of measures which have density proportional to this function, this is a CD with this, some bounds on the curvature minus alpha space. So the important point is the fact that in the case of the Riemannian manifolds, the key object to study is the n Ricci curvature tensor. So the fact that we have exactly this tensor. And Hotta actually was the first one introducing the study relying on this on the theory of Kn convex function, so the entropy functional and all this stuff.
Sorry, may I ask a question? Just
yeah,
to
sure.
Nicola speaking here. So in this case, in this example by Millman, so that is really, the Euclidean distance? So not the Riemannian distance you're taking, right? Is that correct?
Yeah.
I see. Thank you. That's interesting. Okay, thank you very much. Yeah, thanks.
In particular, what Hotta observed is the fact that actually Kn, so the class of CDK infinity spaces is contained on the class of CDKn space for negative values of the dimensional parameter. So in particular, what we are considering is a larger class of metric measure spaces. So what happened, what we did together with Mattia Magnabosco and Gerardo Sosa is to find new examples of spaces, no more relying on the n-weighted Ricci tensor, but on this theory of Kn convex functions. So we fix a parameter which is less than -1, and we consider one-dimensional models. In particular, we found out that when k is greater than 0, the real line with the Euclidean distance and this weighted measure, which is given by this function times the Lebesgue measure, is a CD Kn plus 1 space. Okay, this example is not so interesting, but if we take also k greater than 0, this space is a CDKn plus 1 space. And this space, as you can notice, with this weighted function, this space is a little bit strange because here we have just the half line. We have to consider the 0 because, as we said, we want a complete and separable metric space, because what we want to see are geodesic in the Wasserstein space. In order to have the completeness in the Wasserstein space, we need the completeness on the metric structure behind. So here we have to consider the point 0, but this function is actually exploding close to 0. So it means that if we take any neighborhood, so any ball, any neighborhood around this point 0, the new measure of this neighborhood is equal to plus infinity. The same behavior appears when k is equal to 0. With this weighted function, so n is negative, so you can see better probably that this is actually exploding close to 0. And if you want even a more strange result is in the case in which k is less than 0. And we have the compact interval given by minus pi over 2, pi over 2, with this weighted function, weighted measure, in which the weight is exploding around the 2 boundary points. So the measure of the whole interval, for example, is equal to plus infinity. But this is always a CDK in n+1 space. As you can see from these examples, we are going out from the setting of radon measures that we were considering in the starting theory of curvature dimension cognition. And so it turns out that the class to be considered, the relevant class to be considered in this setting is the one of quasi-radon measure. So what is a quasi-radon measure? Is a sigma-fine measure for which there exists a closed subset that we denote by SM with empty interior. The measure of SM is equal to 0, such that if we take any point inside this SM and any neighborhood of this point, the measure of this neighborhood is equal to plus infinity. What we find in the complement of this set SM on the whole space, so which is an open set, is again a radon measure. So we have the nice property, but just if we restrict to the complement of this set. So our assumption now is the one of metric measure spaces, that are complete and separable metric space equipped with quasi-radon measures. Going back to our examples, in the first case, what we had was a radon measure. So our SM is equal to the empty set. In the second and third case, our SM is equal to the point 0. In the third example, our SM is equal to, again, the set of boundary points of the interval. So at the beginning, we were thinking that these kind of nasty points for the measure were something that was appearing just in the boundary points of our metric measure space, in this case, of our interval. But actually, it turned out, that actually, if we take the example in which we had just the half line, and we reflect this example to the extending to the negative values of the parameter of the space parameter x, what we find is again a CDK n+1 space. But at this point, 0, which is the nasty point for the measure, can be perfectly a middle point of geodesics in the space. Again, we found out that we are actually able to produce spaces in which we have as many nasty points as we want, and this is just taking the compact interval, shifting it, so translating it, and then glue together the n copies. If we have n copies, then we have n+1 bad points, nasty points of the measure, and this again we have that the nasty point can perfectly be the middle point of geodesics. So as you can imagine, this was a little bit a difficult point once we wanted to approach the problem of the stability of this condition, which was, as we were saying, the really first question of Gromov, right? So in the same spirit, we would like to prove that, we wanted to prove that if we have a sequence of CDKN spaces that converts to a metric measure space in the set, saying that it's a complete and separable metric space with a quasi-radon measure, and this in a suitable distance, that what we find at the limit is a CDKN space. So this actually is a true result. So we managed to prove it, but as you can expect, the main difficulties in this proof, first of all, is to find a right notion of distance between these structures in which the measure can explode in some point. Second point is the fact that, as you can expect, when n is greater than 0, this result is proved relying on the fact that the Rényi entropy is lower semi-continuous on the Wasserstein space. But in this setting, we don't have this property. We can just prove that the entropy is weakly lower semi-continuous on this restricted space of probability measures that give measure 0 to the set of nested points of the space. Okay, so this is what I wanted to just to give you an idea of what is this CD condition for negative values of n. A further generalization is the one of synthetic lower Ricci bounds that goes far beyond the setting of uniform lower Ricci bounds. So I start with some motivational examples, and these are really just a selection of the model space we had in mind. And so we start with a smooth Riemannian manifold. And we would like to have a way to describe a lower bound on the Ricci curvature, but at this point, not in terms of a constant, but for example, in terms of a continuous but unbounded function, or in terms of a locally unbounded function, which is in LP for some p greater than the dimension of the manifold over 2. And this, for example, is the case in which we have some conformal transformation in the Riemannian manifold, or some time change with a weight function which is a singular. And the third example I wanted to describe is the one in which we have a Riemannian manifold with boundary, for which the second fundamental form is bounded from below in terms of an LP function, LP with respect to the boundary measure, NP greater than n-1. The reason of the bounds on P is an integrability condition in the theory that we introduced. So the setting now is a little bit changing. So as we were saying before, for our Riemannian manifold, we have a canonical way to describe, to introduce an energy. And also we have seen that also in the case of metric measure space, we can define this Cheeger energy. And moreover, we have also a notion of infinitesimal Hilbertianity, which allows to, that guarantees the fact that the Sobolev space is actually an Hilbert space. These two examples actually can be included in a more general setting of Dirichlet forms. So here, forgetting about this regularity assumption, I wanted just to give you an idea of what is the procedure. So we take a Dirichlet space, which is nothing but a space equipped with a Dirichlet form and a measure. At this point, again, the measure is radon. And the Dirichlet form is nothing but a non-negative symmetric bilinear form in L2, such that the domain of this form that we denote by F is dense in L2 and is an Hilbert space in L2. So once we have the infinitesimal Hilbertian condition on the metric measure space, we have that these two examples actually are falling into this class of Dirichlet spaces. Furthermore, we assume the existence of this Carré-Duchamp, which is an L1 function. So we take, it's a symmetric bilinear map, which goes from the domain of the form times the domain of the form and gives us an L1 function. And this is important because it allows us to represent our Dirichlet forms in terms of an integral of an L1 function. Again, the two examples above are exactly in this case. And so now we change a little bit our approach. So before we have seen a way to introduce a curvature dimension bounds in the case of metric measure spaces. which was relying on a Lagrangian point of view, let's say, because we were considering the entropy and we were looking at the entropy along the geodesic in the Wasserstein space and so on. Here we have this Eulerian approach, which relies on the fact that on a smooth Riemannian manifold, we have the Bochner inequality. And we know that the fact that the Ricci curvature is bounded from below by some constant k is equivalent to the validity of this Bochner inequality for any smooth function. This inequality was generalized in the setting of Dirichlet forms by Bakri and Emery in 1985. And so what they do is for a sufficiently regular Dirichlet space, in the case in which the Dirichlet forms admit a Carré-Duchamp, they wrote this inequality in terms of this Carré-Duchamp and another quantity which is always relying on the Carré-Duchamp. It's actually called the iterated Carré-Duchamp. So they pass from this inequality, which is so a pointwise inequality, to an almost everywhere defined inequality. And our plan, in order to define a distributional value in our setting, is to replace the constant k in this almost everywhere inequality by a distribution kappa, and to consider so this inequality in a distributional point, in the distributional sense, for all the sufficiently regular function f, and for any phi which is greater or equal than 0. So now I give you the definition in order to see what is exactly this term, let's say. So what we define is a Dirichlet space which are tamed in the sense that there exists a suitable distribution for which this Bochner inequality holds true. So here we start with our Dirichlet form. We perturb it using this distribution kappa, and we rewrite this inequality in this form. Actually, in the case in which kappa is equal to k, we find exactly this inequality. So in this case, this kappa is a distributional value lower Ricci bounds, and all the examples that we were describing at the beginning are falling exactly into this setting. And so this represents a way to generalize also the curvature, the lower curvature bound, extending the values, so extending the range of the values, so going from k, which is a constant, to a distribution valued lower Ricci bound. And this is what I wanted to say, and I thank you for your attention.
Okay, so thank you very much, Chiara, for a tremendous talk. So some questions or comments?
I do have a small one, actually.
Yes.
Chiara, you mentioned, so thank you for presenting this result together with Gerardo Sosa and the third author, about the stability of the CD K condition with negative n.
Mm-hmm.
Now, maybe you mentioned this, maybe I Magnabosco, thank you. But so is there a compactness result, Alexandrov?
No.
No.
It's first of all, we have to assume, for example, that what we find at the limit is actually a metric measure space. So otherwise, it's not. There is no way to control how the quasi-radon measure are converging, because they can be at the end you find some weird.
Yes.
And yeah, and moreover, just
this is weaker than CDK infinity, actually, right?
Yeah.
Sorry, my question, yes, boss.
And yeah, exactly. So it's an extension of your paper with Mondino Solare. See. And moreover, it's also
no, but with Andrea and Giuseppe, we made stability, not compactness is
exactly. But
of class lost to Milan in some sense.
But in a sense, if you are not able to prove in the setting.
Yeah, no, you're right. No, certainly, you're certainly right. Sure. Thank you.
Yeah.
Thank you. Nice talk.
Okay, so some other questions or comments?
Sorry, hi, I have a question.
Yes, please.
Are there any results regarding stability when you substitute Ricci curvature for a scalar curvature?
So in the case of, you mean in the case of tame spaces?
Yes.
No, because by now, no. The point is that, let's say that there is a little bit of gap. So at the beginning, for the CD condition, I was presenting the theory following a Lagrangian approach. So in this case, and the gap in the theory is the fact that when CD is with negative dimension, we don't have a way to formulate a Eulerian point of view, as we were saying at the end. So in a sense, for general metric measure space, we don't know how to introduce a Bochner inequality yet. Vice versa, in the case of tame spaces, we formulate everything in terms of the Bochner inequality, a generalization of the Bochner inequality, but we don't know how to pass to the Lagrangian approach. And so we don't know actually how to treat the Bochner condition when you have a sequence of manifolds that are converged or metric measure space that are converged. But it's for sure an interesting question.
But do you think that it will be possible, if I may ask? I mean, Nicola is smiling a lot, so.
Yeah, hopefully yes, but it's, yeah, it has to be a little bit, yeah, in a sense, or try to formulate, as we were saying, something which relies on optimal transport. Otherwise, but in a sense, it's something that for sure, once for example, you keep the distributions which are still nice, let's say, because things cannot explode too much, otherwise at the limit you don't find again the bound from below. But once you can find some way to tame not just the space but also the distributions, let's say, then we expect to have something which is converging. Yeah.
Thank you. That was a very good talk. Thank you.
Okay, so some further questions or comments to Chiara? So, okay, so if not, let's join everybody to clap and say many thanks to Chiara for the wonderful talk. And so now we have, I think, a break. Thank you very much, Chiara. It was a great talk. And I think we are on a break, Maria, so
yes.
you're the leader.
Yes, exactly. I think that I would propose something like 5 minutes break, and then we come back with the second part of the event.
Okay.
Thank you.
Thank you.
So welcome back to everybody. We are ready for the second part of the event and for the second speaker. So I leave the floor to Professor Fantecchi in order to introduce our second speaker of today.
Welcome, everybody. The second speaker of today is Professor Ada Boralevi of the Politecnico di Torino. And she will talk to us of space of matrices with rank conditions. Ada has been a powerful force in GS mathematics for many years. And even now that she's based in Torino, she frequently visits us and enriches us in many ways. Thank you, Ada, for accepting to give this lecture.
Well, thank you. Thank you for the invitation. I'm actually happy and honored at the same time to represent the Mathematiche of SISSA, so women mathematicians. So what I want to do today is somehow try to convince you that the spaces of matrices with rank conditions are worth studying. That's the idea of today's talk. And for that, we are going to start from scratch, like really start from scratch. And we're going to take a vector space. So just consider a vector space that I will call V over a field. And so when I say consider a vector space over a field, there is no assumptions on the field. So just think of the field as a good field, whatever that means. So if you want, you can think of it as just the complex numbers. You can just assume characteristic 0. Actually, characteristic different from 2 is enough in most of the things that I'm going to say. You don't need to have it algebraically closed. Just whatever good field means, K is that. And but another assumption that we're going to make is that the dimension of V is finite. So again, that's not necessary in a lot of things, but let's just assume this for the sake of simplicity, that we have a vector space over a field K and the dimension is finite. And then we have this object, which I'm sure it's familiar to all of you. It should be familiar to my linear algebra students as well. So linear transformation, I call GLV, the group of linear transformations from V to V that are also bijective, so that are also invertible. So this is a group. It's a group, of course, with the composition. And there is a natural action of this group on your vector space that does what? So, I mean, this is the natural action, and the word natural is exactly because it's what you would expect, that how does the group of linear transformation acts on your vector space V? Well, to an element G in your group, you associate the map that takes your vector V to G of V. I mean, the natural thing. And then, of course, because we're assuming linearity, this G is not allowed to do anything it wants. I mean, so for starters, it has to send 0 and 0. I mean, it's obliged to do that by linearity. And then anytime you have a pair of vectors V1 and V2 in V that are both non-zero, you can always find an element of your group, of the linear group, that sends one to the other. So these two things together basically means that things are boring. So not interesting. I mean, under this natural action, as much as it's nice and natural and it's exactly what you would expect, there are only two orbits. So you have the 0 element, which is forced to stay by itself, and then whatever else is non-zero can be sent to each other, like to one another. So nice but boring. So we want to complicate things a little bit to make it more interesting. And in order to do so, the first thing you might think of is take two fast spaces. So now we're going to take two vector spaces that I will call V and W. We're still over our field K. We're still finite dimensional. And then there is a natural action of this group, the Cartesian product of GLV times GLW over the Cartesian product V times W. Again, natural action. So a pair GH acts separately on the component. So a pair GH will send a pair VW into G acting on V and H acting on W. So now things are still kind of boring. I mean, a little less boring, but still not so interesting in the sense that now the number of orbits is 4. So again, the 0 element, the 0 vector in the vector space that is the product is forced to be by itself. Then you have the orbit that I denoted here with the 0 and star, where of all the pairs where the first entry is 0 and the second component is something non-zero, then you have something non-zero, 0, and then pairs where both elements are non-zero. So the situation, and here I used a much more elegant word than just boring, but the meaning is the same. It's not interesting. So what do we have to do to make things interesting? We have to somehow have V and W talk to each other. Because you see, if you look at this Cartesian product acting on the Cartesian product, as I said already, so your element of GLV acts on V, your element of GLW acts on W, and they don't talk, they don't interact. So the way to make things more interesting, and if we do that, I will convince you that actually they are interesting, is that we need to have V and W interact. So in other words, we need to look at the tensor product. So if we look at the tensor product, then things become more interesting. Of course, inside the tensor product, you still have your Cartesian product. I mean, there is a copy of the old pairs VW of the Cartesian product inside the tensor product, and this is via the Segre map. We will see this again a little bit later. But so you can see a copy of the Cartesian product inside the tensor product by simply sending a pair VW into V tensor W. So these elements, this V tensor W, are important elements. They are simple elements, and they are called, actually, I call them decomposable tensors, but another name is, you can call them simple tensors. And not all elements of the tensor product, of course, are going to be look like this. A general element will be of this form, so will be a linear combination of these elements, where I didn't say it explicitly, but basically the idea is that if we fix bases, you can write the elements in a way. I will actually be a little more precise in the next slide. What I want to say now is that the action on the Cartesian, so you can see it in two different ways. So you can either define the action of the GLV times GLW on the tensor product as I wrote down. So a pair GH acts on an element this way. So now you see, we still have that G in GLV acts on VI and H acts on WI, of course. I mean, it wouldn't make any sense otherwise, but now they interact. So this map here is not a linear map, it's a bilinear map. If you want, it's a quadratic map, actually. So the bilinearity here makes the two words interact. And so what I was going to say is you can define the action this way. It's a good definition. You can check that it's a good definition. You can also define the action on the decomposable tensors and then extend bilinearity. It's up to you. And so what do the orbits look like? That's the question. And the answer is, this time it's interesting. At least I want to try to convince you that it's interesting. So in order to do so, I need the concept of a rank of a tensor. So since here our tensors are basically matrices, I will show you how and why. The rank is easy to define and also to compute. So let me be more precise. So we're going to fix bases. So we are going to fix a basis V1, Vn for V and W1, Wm for W. And then, so what happens basically is that if you take all the elements of the form Vi tensor Wj, with I from 1 to n and j from 1 to m, so this is a basis for V tensor W. So I somehow already swapped something under the rug, but just you can prove that this is a basis. And then this means that any element in the tensor product can be written as, of course, a linear combination of the elements of the basis. That's not a big deal. Where now, so you have these entries here, they are scalars and they depend on two indices. So you can look at this Tij as a matrix, as an n by n matrix. So you can actually look at T as an n by n matrix, and then you can define the rank of your tensor as the rank of the matrix. It turns out, it's not hard to prove, that the rank does not depend on the choice of the basis. So whatever choice you make, your rank is uniquely defined. And the rank actually is so that there is an equivalence. So this is completely equivalent to this, where what does it say? So anytime you have a pair of tensors, so two tensors, T1 and T2 in V tensor W, then you get a pair in the group, so an element of the group GLV times GLW, sending one to the other, if and only if the rank is the same. So this time, you see, the description of the orbits is much more interesting, because this time we have a filtration of orbits, where we have k orbits, with k, of course, being the rank, so a number that moves from 0 to the minimum between n and m. And somehow this makes things much more interesting, because now, you see, it's not like just 0 non-zero. It's actually, you have this rank condition, which makes the description very nice. So now the action is still a natural action, but the spaces of matrices, well, let's not talk about spaces of matrices yet. Let's just say these matrices with rank conditions now correspond to orbits under a very natural action of a very nice group. I can give you actually a more geometric approach as well. So this, if you want, you can call it the linear algebra approach, or actually, I wouldn't say linear algebra, multilinear algebra approach to the description of matrices with some rank conditions. But I can give you, of course, a more geometric approach, a more geometric description now. So let me take again this Segre map. So now I look at it from the projective point of view. If you don't like the projective space, you can still think of it as in the affine world. It doesn't really matter. So this map sends your Cartesian product into the tensor product, and the image of this map is the Segre variety. So what is the Segre variety? The Segre variety is the image of this map and corresponds to the composable tensors. And up to now, I already told you what I mean. That is tensors of rank 1 inside P of V tensor W. Now this I have to justify. Why? Well, first of all, since I'm talking to a wider audience than usually, when I say variety, I don't want to complicate things. You can just think of the zero locus of a system of homogeneous polynomials. You don't need that much more structure for what I'm saying. So a variety is just the zero locus of a system of homogeneous polynomials. So the fact that the image of the Segre map, so the Segre variety, corresponds to the composable tensors, I guess it's just by definition. But in fact, these tensors or matrices are exactly the ones of rank 1 inside your tensor space. Why is that? Well, first of all, you can see it in coordinates. So if you look at the whole situation in coordinates, actually, if you look at what does the element V tensor W look like, you can actually see that once you fix basis and you look at the coordinates, it is the product of the if you want, oh, this is an M. So you look at V as a column vector, you look at W as a row vector, and then you take the row column product, which in this case being a column row gives you a matrix where you can see that all the rows are multiples. So this is a matrix of rank 1. So you can see it explicitly in coordinates using the definition that I gave before, that decomposable tensors have rank 1 as matrices. But you can also give a different approach. So you can actually give, let me just write it here, an alternative definition of rank. So you can actually declare decomposable tensors to have rank 1. And then all the other ones, so a tensor T, which is not necessarily decomposable, the rank of T, you can define it to be the minimum K such that you can write T as the sum of K decomposable tensors. So again, decomposable tensors have rank 1 because you can write them as the sum of one decomposable tensor. And all the other ones, the rank correspond exactly to the minimum number that you need to write your tensor as a sum of decomposable ones. Now, in the case of matrices, things are very easy. These two definitions are completely equivalent. In general, so as soon as you go to higher dimensional tensors, you go from order 3 up, things become much more complicated. And actually, this is the good definition if you look at tensors of order 3 and up. But for us, in the world of matrices, things are interesting. I'm not saying otherwise, but they're easier, much easier than what happens for tensors of higher order. So the Cheeger variety corresponds to decomposable tensors, which are tensors of rank 1. And now, so if I want to give this geometric interpretation to the other ones, to the other tensors, not just the ones of rank 1, I need to consider the secant variety. So what is the secant variety? Let me introduce you to the secant variety. So this Rth secant variety is what? So I take x1, x2 up to xr independent points on my variety, on the Cheeger variety. I can do this for any non-degenerate variety, but just let's do it on the Cheeger. I take r points. I take the linear span of these r points. So this is an r-1 space. And then I take, so this is an r-1 secant space to my Cheeger variety. And then I take the union varying on all these r points, r independent points on the Cheeger of all these linear spaces. And then because I don't want to consider only the secant spaces, but I also want tangent spaces, I take the closure. So the closure here is because, well, what is the limit of a secant space? It's a tangent space. This we teach to our calculus students. And here, actually, the closure, you can take it in the Zariski topology or in the Euclidean topology, you get the same thing. So the elements of this secant variety correspond to my matrices of rank at most R. So I want to explain this a little bit better by drawing for you a beautiful picture. So let me just kind of draw for you the case of rank at most 2, so the case of secant lines. So you get somewhere you have your Cheeger variety, which is this little hat here. So this is my Cheeger. And we live inside the world of, inside this big projective space, which is, if you want, just n by n matrices. And then, so what are secant lines? So I just take all the lines that are spanned by 2 points, 2 independent points, x1, x2, of the Segre variety. And then, I take the union of all these lines that are all secants in 2 points. And I also, as I was saying, I also want to take the ones where the points are coincide, so the tangent lines. That's why I take the closure. And so what does an element in a secant line, on a secant line, look like? So if you have here a y that is in the line spanned by x1 and x2, well, so this is still a matrix. We're in the world of two tensors. So this corresponds to a matrix. And this is a matrix that is basically the sum of two rank 1 matrices. And you know that a matrix is the sum of two rank 1 matrices if and only if the rank is at most 2. So the rank of y, seen as a two tensor, seen as a matrix, is at most 2. And so this is the picture. Well, it's an idea of the picture for secant lines, but you can take secant planes, you can take secant 3 spaces, and so on. So what you get is a geometrical interpretation of matrices of bounded rank, if you would say, or matrices with rank condition. And in general, you will have that your sigma k, so the kth secant variety, will live inside the k plus 1 secant variety. So what you get is, again, a filtration of orbits. They're basically the same orbits. And here again, if you play the same game for higher order tensors, things become much more complicated, but not here, where basically you have rank 1 matrices that correspond to the Segre, and then of course they live inside the matrices of rank at most 2, that live inside matrices of rank at most 3, and so on. And then at some point, you fill up the whole space. You fill up the whole space. At some point, of course, the generic rank of an element will be the maximum, so the possible maximum rank, so the minimum between n and m. And this is, so n is, in this case, is just the minimum between n and m. So at this point, I hope at least that I have convinced you that the structure, the world of matrices, if in general it's interesting, but especially if you look at matrices that have some rank conditions, you get a beautiful algebra, beautiful geometry, beautiful structure, representation theory, you name it. But there is a very nice structure, and I hope that by now I convinced you that it is interesting. And the way that I want to study these spaces is by studying linear spaces that have a certain position inside this world. So finally, after almost half an hour that I've been talking, I am ready to give you the definition of space of matrices with rank conditions. So let V and W be, I'm going to read it with you, then I will give you some, I will make some comments. So let V and W be finite dimensional vector spaces over a field K. So the same situation as before. A vector subspace, so A is a vector subset inside this tensor space. Let's just ignore for a second this. Is a space of matrices of bounded rank if all its elements have rank at most something, and usually we use the letter R for the rank, and constant rank if, guess what, all the elements have constant rank equal to R, and at this point you have to add the word non-zero because, of course, the 0 element will have rank R. We have the rank 0. So basically what we're doing here is we have this nested orbits, and then, so this would be the rth secant, sigma r, this will be the sigma r minus 1, and everything in here is inside sigma r plus 1. And so if you look at spaces of bounded rank, it means that you're looking at linear spaces inside here. You don't care what is the intersection with the lower orbits. If instead you look at constant rank, then you look at spaces, linear spaces that live here. So they live inside your Rth secant variety, or if you prefer, they live inside the orbit under the Rth orbit under the action of your general linear group, but they don't touch the sigma R minus 1, which actually, for those who know, happens to be the singular locus of this variety, but we don't really care about that now. And then what I mentioned here is something that I hadn't mentioned yet, which is there is also a natural isomorphism between elements in the tensor space and linear maps from the dual of V to W. So you can actually construct this, once you fix basis, you can construct this isomorphism explicitly. I don't want to do it now. I can tell you if you're interested, it's not hard. But it's just, if you want, you can think about it as just that yet another way of thinking F as two tensors as matrices. Because of course, morphism from two linear maps from one vector space to another, if you fix basis, they're just matrices. So I want to concentrate from now on constant rank. The reason why will become clear in a second. So now I would say, if I want to say just like Chiara earlier, up to now somehow, I haven't finished the part of general results, but I think I have somehow, I got to the point where you should know a little bit of geometry to keep on following what I say, but not much, just a little bit. I was hoping that what I said up to now was somehow understandable by anyone, not just geometry people. So the interest in this space is actually is classical. And it's classical, and also one feature that is, I think, very interesting is that it bears to completely different contexts. So of course, we are in the realm of linear and multilinear algebra, but we can use algebraic geometry tools to study, and this is what I want to tell you in the rest of the talk. But you also have connections with differential geometry. You have connection with mathematical physics. You have connection with numerical analysis. So mathematical physics, for example, there is some connection with some special system of conservation laws that have an interpretation with the space of matrices of constant rank. Numerical analysis, on the other way, you can use some results on spaces of matrices of bounded rank to prove some optimization results, and so on. So it's a subject that bears to different contexts, and by different, I mean like a good variety of contexts. And so what are the main questions that you can ask? So the first thing that you ask yourself, well, that people ask themselves, that mathematicians ask, is how big the spaces can be. So since we are asking for linear spaces, and we are, let me just do this beautiful picture. I want to take it here. So here. So since we are studying these linear spaces inside these orbits, it's very natural to ask yourself, how big can you get? Like, how much space do you have? And then the second very natural question is, do I have relations on the possible values of the parameters? So what I mean is, say that I want to fix the size of the matrix and the rank, then how big can I get? Or maybe I want to fix the dimension, and what type, say I want dimension, like what type of three-dimensional spaces I can find, do I have to fix a rank? Do I have to have some conditions between all these parameters? Then there is, of course, the usual obsession of mathematicians, classification. So once you know that some objects exist, you want to classify all the examples or classify the spaces, of course, and you will do it for fixed values of the parameters. And then there is a problem of constructing explicit examples. And the problem of constructing explicit examples, of course, I mean, I decided to divide this into three main questions, but of course they're all interlaced. By constructing explicit examples, you help the classification. You can also prove some results on maximal dimension and so on. And as I was mentioning before, algebraic geometry appears as a natural tool in their study. And this is not news. So what I'm going to say at the beginning is nothing new. It's results from the 80s and 90s of last century. So the first one who perhaps realized that you could use algebraic geometry to study the spaces was Sylvester. And with this, Sylvester is actually an algebraic and a linear algebraist. So it's not the Sylvester that you think of. And this is actually 1986, not 1886. So just to be, so it's old, but not that old. So this approach was carried on in all the 80s and 90s by several works by Westwick, another linear algebraist in the 80s and 90s that I will tell you about a little bit more in what follows. There is a seminal paper by Eisenbud and Harris from '88. And then, for example, there is another important paper by Illich and Landsberg from '99 and others. In particular, when I say that algebraic geometry appears as a natural tool in their study, what I mean is that the relation with vector bundles on Pn and their invariants is particularly useful in the study of these spaces. And this is where the hypothesis of constant rank comes into play, in the sense that you can actually do similar reasonings, and people did, with bounded rank, but then you have to work with sheaves, not just with vector bundles, so coherent sheaves. So things are slightly more complicated, but not bad, but vector bundles have much stronger properties that you can use if you study constant rank spaces. So how do you use vector bundles to study the space of matrices? So the first thing you want to do is you fix bases everywhere. So you fix bases in your space, vector space V in W, and also on your subspace A. And once you do that, basically what happens is you can see A, you can see the space A as a matrix itself. So this is basically what happens. You can look at A as a matrix itself, but now of course the entries are going to be linear forms in whatever the dimension of A is, number of variables. And once I get this matrix whose entries are linear forms, that I will call simply a linear matrix, I can look at it basically as a map of vector bundles. So how? Well, at this point, I can interpret the kernel, the co-kernel, and the image of this map as vector spaces, of course. And the point is that as you move, the constant rank hypothesis makes it so that these vector spaces don't change their dimension. So there is no drop or there's no jump in the dimension. So these are vector spaces that vary smoothly over all your Pn, which is what I will call from now on the projectivized version of my space A. And so you have vector bundles, that's the point. So in other words, you look at your A inside V tensor W as a morphism with the isomorphism that I was mentioning before. And so this is exactly a linear matrix. So a matrix whose entries are linear forms in n+1 variables. And this induces a log exact sequence of vector bundles on Pn, where so you have, this is your kernel, this is your co-kernel. And then if you want here, you also have an image. And what happens is that the computation of invariance of these bundles already yields restrictions on the values of the parameters and actually gives you bounds on the dimension. So actually the properties of these vector bundles give you a lot of information. The very first kind of information that you get is studying invariance of these bundles. And let me show you an example. So let us define this LABR as the maximal possible dimension of a space of matrices of size A times B, A by B matrices of constant rank R. So this is LABR. And then I have this roundup of results that are actually, it's on purpose that they are in a smaller font, because I don't really need you to read all these results. What I just want you to realize is that just from the computation of invariance of these vector bundles, you get a lot of bounds on the dimension. So those are, again, a roundup of results by Beasley, by Sylvester, by Westwick in the 80s and 90s. And again, there is no need to read the details of this. They're just different bounds on the dimension with some hypothesis on the rank, on the dimension of the matrix. In particular, actually, up to here, they're just any size. And then if you go down here, you have square matrices. Why do we concentrate on square matrices? Well, because in fact, and this is, I hope it's clear, in general, the problem of finding an optimal bound is open. So the computation of this number, if you want, it's open in general, completely open. So what do you do when you have something that is completely open and you don't know how to deal with it? You put some extra hypothesis. So the first very natural extra hypothesis that I can put is that the matrix is square. So you basically get rid of one of the parameters, because now you have an A by A matrix. And you can say some more things, but still in general, the computation is open. In general, the problem is open. And now I want to tell you that people are still working on this. So not just me, but I want to keep going with this roundup of results. And the first result that I want to quote is a paper by Philippe Elia and a student of his, Menegatti, from 2000. So this is not 1916, this is 2016. So this is the reason why I'm quoting this paper is because it's a very interesting paper, and also because I want to show you that people are still working on this. So this is not old stuff. I mean, it's not new, but people are still working. So this paper actually is very interesting because the authors make a connection with a very interesting and long-standing conjecture about uniform vector bundles. So uniform vector bundles are vector bundles that have the special property that no matter where you restrict them on lines, they are the same. Let me just be vague. I know I'm being vague, but I don't need to tell you more details. So there is a very important and difficult long-standing conjecture that relates uniform vector bundles to homogeneous vector bundles, so homogeneous under the action of some Lie group. And so they were able to make connection with the spaces of matrices, of square matrices of constant rank. And in particular, they computed an effective value of this maximal dimension for a less or equal than 10. So now I hope that by underlining the fact that this result only works for up to 10 by 10 matrices, I don't want to diminish their work. I just want to underline the fact that this is in general still completely open. But they do a conjecture that involves some special values of this bound. And basically the conjecture is true if the conjecture of the uniform vector bundles famous conjecture is true. So this would be a consequence of this conjecture, if ever someone proves it. Then we restrict more. We restrict ourselves even more. So we passed somehow in this roundup of results, we passed from any size matrices to square matrices. And we have seen that it's still too wild. So what we do is we restrict ourselves even more and we put on some extra symmetry properties. So we limit ourselves to square matrices that are either symmetric or skew symmetric. Then if you work with symmetric or skew symmetric matrices, you can actually get a very, very nice description of the orbits and the secant varieties that I was explaining earlier about the Segre for other varieties that are, well, in the symmetric case, at least, things are much more well known. So in this case, you talk about, I will just mention the names, the Veronese variety and Grassmannians. But what you do is you restrict yourself, you have more tools. In particular, already for spaces of matrices with these extra symmetry properties, you have more tools, but one more restriction, and now this will be the last restriction, is that you actually limit yourself to co-rank 2. So you have square, you have symmetric, you have skew symmetric, and the rank is 2 less than the dimension. And the reason is that in this case, your vector bundles have rank 2, and rank 2 vector bundles over the projective spaces are much easier to study. That's the only reason. So in this paper that I had already quoted by Illich and Landsberg, they actually completely solve the case of symmetric matrices of constant co-rank 2. They find that the maximal dimension is 3, affine dimension. But another very interesting thing is that they make a connection with differential geometry and with the generalization to projective varieties of the second fundamental form. So they make a connection between the space of matrices of symmetric matrices of constant rank and the second fundamental form of projective varieties that have degenerate dual. So the dual variety is smaller than what you would expect. So since the co-rank 2 case is solved for the symmetric case, then people started looking at the skew symmetric case. And the first interesting non-trivial case is actually 6 by 6 matrices of constant rank 4. And for that, there is a paper by Laurent Manivelle and Emilia Mezzetti from 2005, where they give a complete classification of these spaces. There is another paper a few years later by Emilia Mezzetti and Lucia Fania, where they work with the same problem, but they take bigger matrices. And up to now, people have really worked on these problems, working with more or less classical results on vector bundles. So, oops, sorry, that was the pencil. I got excited because now finally I'm talking about my results. So in this few last minutes, I want to tell you a little bit about my own results. So we somehow pushed the interplay with algebraic geometry a little bit further. So we took the relation to the next level by introducing derived category tools and instanton bundles in a paper with Emilia Mezzetti and Daniele Faenzi, and then another one just with Emilia, so 2013 and 15. So this is the long exact sequence that I was already showing you before, that is induced by the matrix. So anytime you have a matrix of constant rank, you get this long exact sequence and you get these two vector bundles. But in fact, if you work with this special case of skew-symmetric co-rank 2, this K and N are basically the same bundle, almost. So what we did is we looked at this not just as a two extension, not as just as a long exact sequence, as much as just a map in the derived category of coherent sheaves, on the bounded derived category of coherent sheaves on Pn. And using this point of view, we were able to reverse the construction. So what does this mean? It means that if I hand you a matrix, a linear matrix of constant rank, then you get the vector bundles, and that's easy. What was not easy, and in general, it's not easy, is to get the linear matrix starting from the vector bundle. So this is what I mean by reversing the construction. And somehow we found that when the vector bundle satisfies some specific conditions, so the invariants satisfy some specific conditions, and there are some cohomological non-degeneracy condition, then somehow the matrix, the linear matrix, is hidden in this space, or better yet, there is an element whose cone gives you the matrix. And then in the paper with Emilia, later we actually used these results together with some results on globally generated vector bundles to focus our attention on just the projective plane, and we gave an almost complete classification of all the cases of skew-symmetric matrices of constant corank 2. Now, the result that uses this derived category is, it's a nice result and it's very elegant, but it has a very big problem, that is, it's not constructive. So where are the matrices? And this is basically the very last things that I want to tell you. The matrices are hidden somewhere, and we were able later on to prove how you can construct them using instead commutative algebra methods. So while trying to understand how we could effectively construct these matrices, we realized that actually, if you work with commutative algebra, you can get some interesting result. This is what we did with Daniele Faenzi and Paolo Lella a few years ago. And again, I don't want to go in the detail of this, but the idea is that linear matrices are cooked up via two finally generated graded modules over the ring of polynomials that have a linear resolution up to a certain step. So let me just explain, wave my hands and add things to this picture so that I can tell you exactly how you find these matrices. So basically, you assume that you have two graded modules, and they might not have linear resolution, but you can truncate them at the right point and get a linear resolution up to a certain step at least. But you might not have control on how big these matrices are. For example, you have this and you don't know exactly, you might get these Betti numbers to be too big. But if you have another module here, G, and the surjective map from E to G, then under some conditions, and I don't want to get too technical, the kernel will also have linear syzygies. So this is basically the idea. There is a few technical conditions that make it so that you start from your graded modules, you look at the resolution, you make it linear, and then somehow you can perturb the module and get a nice linear presentation that has the same constant rank as before. And of course, now the size is what you wanted. So I understand that I'm just basically just giving a rough idea, but so somehow you can reverse the construction, and the classical construction of going from a linear matrix to a vector bundle can be reversed, and it can be done via derived categories, but then it's not constructive, or you can use graded modules and truncation of these graded modules. And then this is maybe a little less elegant if you want, but the advantage is that it's not only constructive, but it's algorithmic. And we have Macaulay 2 packages where you can construct as many examples as you want. And so this is the very last thing that I wanted to tell you. So can we go beyond this? So why do we limit ourselves to linear spaces? And the reason is there is no reason. So in particular, in a very nice, easy case, we were able, together with Lucia Fani and Emilia Mezzetti, and this is the latest, I hope not the last, but the latest result that I want to tell you about, we were actually able to study quadric surfaces inside a particular orbit. So in the case of skew-symmetric matrices of, well, just 6 by 6 skew-symmetric matrices, the situation is very easy because a 6 by 6 skew-symmetric matrix can only have rank 2, 4, or 6. There is not much else. So if you look at Costa rank 4, then you have some P2 in there, some P2, some planes. You cannot have P3s completely contained in that stratum, but you do have some quadric surfaces. And what we did with Lucia and Emilia was exactly to describe using, again, vector bundles. So we haven't changed completely because we still use the results on vector bundles on the quadric surface, but it is possible to actually study other types of non-linear spaces inside these orbits. So this basically ends my discussion. So I hope that I got to the point without being too technical. I've tried to be as least as possible technical, with the result that I didn't go into the details. So probably if you're expecting some interesting details, algebraic geometry details, you were disappointed. But I hope that somehow you all go home thinking that spaces of matrices of bounded and constant rank are interesting. That was my goal. And I thank you for your attention. And I finish with a little bit of a humorous, but also controversial note on, since we are talking about women in mathematics, and this is the International Day of Women in Mathematics, let me mention that even if it's pink, we still have a glass ceiling above us. And I'm done. Thank you.
Thank you, Ada, for your lovely talk. And are there questions or comments?
I have a question actually for Professor Boralevi. I'm not in the field actually. I mean, as you know, I am in numerical PDEs analysis, but I know that this field of algebraic geometry is really used in numerical analysis, like linear algebra numerical analysis for, optimization, as you said, and the preconditioner analysis. And I mean, since I'm not in the field, maybe it's a silly question, but you know, you showed all the results about that magic number of dimension of the space of matrices that have some rank, okay? And okay, I get that depends on the dimension for sure, but there in the any site exactly, I saw this alpha, right? Somewhere. So there is another parameter alpha, and so I was wondering if you can comment a little bit about this parameter.
This is just actually this is an interesting example because it's what led us to study some particular example. So this alpha is just saying that anytime it's basically just to describe the size of the matrix. So this is matrices of co-rank 1. So you have rank is alpha times S, and the size is alpha S plus 1 and then something bigger. So they look like this, and the co-rank is 1. And actually this was, it's by itself because it's the only case that is left out by these few results above. So this was treated separately in a paper where somehow Westwick, so these three are almost, they are all from Westwick. And he left out, they leave out this result. Maybe it's because of the parameter. I actually don't know why exactly this was so much harder. But so somehow he was not happy about having this case left out, and he wrote an entire paper just about this case. And it's basically a paper where he shows an example that proves that this is the maximal dimension. And he basically shows this example in the first page, and then it takes him like 20 pages of computations to prove that the rank is constant.
Okay.
And this is one of the examples that actually now, thanks to the Macaulay packages that actually, to be honest, Paolo Lella wrote, you just need one click now, and you can use line bundles on PN, and you can construct as many as you want. But I think that the reason, maybe you're right. Maybe the reason is that there was this parameter, and that's why the case was harder. I don't know this.
Okay, thank you. I was just wondering how the matrix was, right? Because in preconditioning analysis, it's very important to look to the matrix and understand actually how it looks like. So I was wondering what was the matrix.
It's basically just that's how they are related, the size and the rank. But the point is that the co-rank here is 1 for us. The point is that so we can use a line bundle. So a bundle of rank 1. That's
okay. Thank you very much.
Thank you.
More questions or comments?
Barbara, we see just very dark. I see just
let me see.
Oh, here you are. Oh, no.
I am there?
No, now it's dark again. Now we see you.
Okay, great. No, the problem is I cannot see myself. And so I have to guess which camera is being used, and there's a 50-50 chance. Okay, more questions. Actually, I have a question, which is about exactly what you just said. What is the impact of computer packages? You know, the fact, what do you think is the impact of the existence of these computer packages on this kind of research? And by impact, I mean in either way. On one side, that we use computers to do the math, and on the other hand, that we use the math to understand computers.
So in the case of this example that I was just quoting, it just makes things easier. So you now have, like, you really have to just push one button instead of doing 20 pages of computations to construct this example. In the latest paper with Emilia and Lucia, we actually used a a lot of Macaulay to algebra to construct our examples. And there it was really just a question of using the power of the computer as a computer person. So we had to compute some projections, and then you had to compute some resolutions, and then, you know, it's maybe you could do it with some Grabner basis work, but it would take you, well, it would take me weeks. I don't know, maybe take you less, but on the other hand, so this is how I would say computer packages help us. But on the other hand, and this somehow relates also to the question of Maria. So I have a paper with some numerical analysts actually, where they were interested in some optimization problem where they had to represent some polynomials as the determinant of a matrix, so a determinantal representation. And they were, of course, looking for the fastest way and cheapest way to do it. And we were able to use some results on, actually by Eisenwood and Harris, so old results, but then we were able to use results to implement and to help them with this algorithm. So I guess it goes both ways.
Thank you. More questions?
I have a question, but it's not that smart.
Oh,
That's a great way to ask my question, by the way.
Question, just stupid answers.
You draw a parallel with the second fundamental form.
Yes.
So what so when the second fundamental form vanishes, you get totally geodesics of manifolds, right? That they inherit the geometry. So in your setting, what's the analogous situation?
So in my setting, the analogous situation is that what happens is that, so if you have a projective variety and you take its dual variety, so you take all the hyperplanes that contain the tangent space to your varieties. So this lives in the dual space, and you expect it to be a hypersurface. Well, yes, a hypersurface somewhere. So you expect it to have codimension 1 in your dual projective space, but sometimes they don't. So those are the so-called varieties with degenerate dual. And what Illich and Landsberg proved is that there is an equivalence actually between having degenerate dual and having the second fundamental form that is a linear system of symmetric matrices of some specific rank. So I have to be honest, I don't remember the exact details of this, but this is the idea. So there is exactly an equivalence between having degenerate duals and the second fundamental form of these varieties being a linear system of symmetric matrices of a constant rank. So that's how it works.
Thank you. Thank you for interesting talk.
More questions or comments?
No, but I have a comment. I think we should, again, thank the organizers for this nice.
We certainly should thank Maria.
Yes.
She did a fantastic job.
Maria was the major organizer, yes.
Thank you. I mean, I thank you all. I thank the speakers. Actually, now was programmed something like a discussions with the speakers. I don't know if we have time, but maybe if someone of the audience, I see also PhD students between the audience have some questions to the speakers about the research life. I don't know, something like that. I think that they can ask if the speakers are okay with that.
Yes. Or also if the audience is shy, I think I wrote here. Yeah, that's you can use a more private mean.
Maybe we should stop recording indeed if we want the younger people to participate.
Okay, but actually maybe I can start And I think there is no problem in recording this question. Like I'm finishing, so basically my question is about how did you feel when you finished, and how did you feel when you started an academic career? And now that you have seen some other universities, some other institutions, I would like to understand what is the feeling about gender gap also in other institutions, also, you know, beyond Italy, because this is, you know, my vision now. It's only about university in Italy and SISSA in specific. So if you want, comment a little bit about that to both the speakers.
Chiara, if you want to say something.
Actually, in a sense, that here in Germany about the gap, the gender gap, I know that they have a lot of rules, but I think that rules are always controversial a bit, no? Because they are trying to reach like half and half of a male professor and female professor, and yeah, in a sense, but in a sense, I really don't see a difference between all the university in Italy, I think, and for sure now there are many European rules, regulation in order to also in conferences, in order to have an equality between the number of speakers. But in a sense, at a certain stage, I think it becomes a little bit a philosophical question. No, do we really need this kind of stuff, or it would be better like to have these things without any rule, or like I don't know. And as for like the career opportunities, I think in a sense. A little bit, I think that we are a little bit all in the same boat, and and it's like now I think it's more the problem that the number of positions is really reduced, or better, there are not so many positions open in this period. So I don't know if it is the Corona crisis or whatever, but yeah. Ada, probably you have more to say, and you have also.
Well, I mean, so I have to start saying that I, at least at the beginning of my career, was very lucky because, well, my advisor has always had women students. And also, I think his attitude, Giorgio Ottaviani, his attitude is very, I would say he's never made any kind of discrimination against any of his female students. And I come from also a family of, my mom is a professor, and so I was well aware of what problems you could have being a woman in academia. I have been quite lucky, but so one thing, for example, is that somehow you're always the secretary for whatever kind of like there is a meeting, and your opinion matters. I'm not saying that it doesn't. So your opinion matters, and it matters as like at the same level of the other ones. So I'm not saying that they don't listen to you, but then if someone has to like take notes, then that's you as a woman. So this is, for example, this is and this is so I've been in I've been in the US several years. I've been in the Netherlands. I've been in Poland. I would say that the Netherlands is maybe the best country out of all these, and Italy regarding to women problems. They have like a very strong policy now with for what we call quote rosa, so hiring just women, and they have been having by Antonio, and they have been they've been having this only female position, like a reserve for female positions for a while now. I think they were among the first, okay. At least in Europe.
Okay, so they have a little bit longer history.
I would say that, for example, from this point of view, Netherlands are much more advanced than, for sure, France and England and Italy. You can do it. It's harder, I think. But I think that now we are, well, first of all, it's hard for everyone, like Chiara was saying. And also, I think that even in Italy now we're starting to have some kind of attention, which doesn't mean that they will stop asking you to be the secretary, but maybe they will also give you a position at some point. We are doing what we can with Barbara and Valentina Beorchia. We are organizing these summer schools where we only have women speakers, lecturers, but it's not a women in algebraic geometry kind of thing. It's just, so they are excellent algebraic geometers. They're not women algebraic geometers, but sometimes you have to be precise. So I don't want to be too controversial, non voglio fare polemica, but you are not exactly equal to men.
Mm-hmm. Okay.
But it's not so bad, but you're not exactly equal. And you will never be, at least not in, I think I will not live to see that.
Okay.
And Barbara is nodding, but I don't have children, so this is also help me if you want. Not yet, at least, but I know, for example, that, well, Barbara can tell you, but like breastfeeding them was not so easy, for example, for Barbara, or this kind of problems.
Okay.
But I think it's getting better.
Yes, I mean, I see a hope at least, so it's, thank you.
Going better for society in general, because academia is just something which is immersed in society, no? So I think that really this the thing which is really different from one country and the other is really the mentality, which is something that is like inside a person without the person knowing it. So it's not something that is made on purpose by a man or also a woman, because also sometimes women are the first against women, no? And so I think it's really something which depends on the society. If you go to Netherlands, it's something that you don't see just in academia. You see in shops, you see everywhere. Like there is plenty of fathers with children at the park. If you go to a park in Trieste, there are just mothers with children, no? Or some rare father. And so this is something that is really, I think, strictly related to the mentality and how family are growing up children and everything. So.
And also, I think another, maybe I don't want to abuse of your time, but another thing that I think we have to deal with is the other side of the same thing, which is now positive discrimination. So I see it from a different point of view. So my partner has had now several occasions where he didn't get the job because some woman got the job who was maybe, I mean, not worse than him, but maybe at the same level because of this idea that you should hire more women. So this is what is called, positive discrimination. And I think that it's hard for women as much as for men to accept this. Like I'm not sure how I would feel knowing that I got the job just because I'm a woman.
Yes,
but I think that it's necessary. I mean, we have to go through this and then hope that at some point,
Yes, I agree with you totally.
Positive discrimination is what, from where I come from and Barbara comes from, is called Poggio e buca fanno pari. So, you have to level up, let's say. But I understand that now it's, I mean, you still have, for example, in my department, since, you saw a little bit of my department because you gave a talk recently. So associate professor level, we're almost 50-50. But there, we only have 2 ordinary professor, women ordinary professor. No geometry professor is ordinary. So, I mean, it is what it is. I don't know if I gave any kind of a significant contribution to this, but a few random thoughts.
Thank you. Thank you very much for this discussion. I don't know if there are other questions from the audience.
I do have one question if we still have the time.
Yes.
So both of you were part of SISSA community at some point. I know there's a long list of answers, but if you will have to pick one thing that your male colleagues could have done and you wish, even in hindsight, that we had done, but we didn't, what would that be? I don't know if I made myself.
Yeah, I understood the question, but it's a hard question. I'm thinking, but
I'm talking at every single level, like even at lunchtime or I don't know.
Well, I mean, at least for me, this thing that I mentioned before, it really bothers me that I have to be the secretary for everything. Like, for example, even we have a colloquia committee in my department, and it's 4 people, and somehow I have to be the one who organizes coffee breaks, which is stupid. I mean, it's not something it's okay. It's not that big of a deal, but it's somehow implicit that because I'm the woman, I have to organize this kind of things. This is something that I think could be avoided, but it's a lot of times it's not. So at least for me, that's what. And also, I would say that women are expected to do a lot more in terms of teaching for some reason that I'm not sure why, but it happened to me. So maybe because you're supposed to have like a maternal attention to students. I don't know. But this is something that bothers me as well. Chiara?
Yeah, probably this thing of the secretary, yes, I remember. But I think it's again something which is cultural, because I remember that I was in SISSA, I had the office in the 7th floor.
Chiara, did you see that Nicola went away so that you can say whatever you want?
Yeah, okay, but in a sense I don't have anything to say against that. But I remember that there was this Russian postdoc who we were waiting for the elevator in order to go to Mensa, and I was asked if I'm a secretary, and I was no, I'm actually a PhD student because in this floor there are the offices of PhD students, not just the secretary office, no? And it was a little bit strange as a question. Then yes, sometimes there are many little things probably that make you feel that actually it's more an ambient for men than for women. Like when in conferences there are like 100 speakers, and so that let's say also just the bathroom of the woman turns out to be the one of the common one, because there are too many male attendants, and so and there are probably just 3 or 4 women, and so they said, okay, but so we need 2 toilets, and let's turn the one of the female into a mixed one, just because we have less queue, right? So this thing actually sometimes happened, and also because in a sense I experienced like something like this. So it's by the way, Nicola left, but we are still recording. So no, in a sense, it's there are some little things that makes you feel that actually probably the real there is some gap between the two things. But okay. in a sense. I think again, it's something which is not inside just academia, so it's really difficult but not impossible to make things going better. And I hope also that they are going to be better.
Thank you.
Oh, thank you, Raphael. So hopefully we can all see each other in person.
Yeah.
Yes. Yes. Okay. So it seems to me that there are no more questions for the speakers, and it was a beautiful discussion. So I thank once again Chiara and Ada for this discussion. So Dr. Rigoni and Professor Boralevi for this discussion. And I thank all the audience for being with us today. And this was really important to me. So thank you. Thank you very much.
Maria, is Raphael still here? Raphael, I just, when Maria said Dr. Rigoni and Professor Boralevi, I just realized something. So one thing that I hope people would, my students especially, would stop doing is calling me Signora. Why do they call me Signora Boralevi? I'm not Signora Boralevi, I'm Professor Boralevi. And they never call any man Signore.
Yeah.
Yeah, that I have noticed.
Yeah, so that, yeah, sorry, just...
That's okay. Or probably...
When Maria said professor, I got, yeah, and it happened to me a couple of times to tell my students I'm not Signor. I mean, you know.
But actually also like, in a sense, something that made me think a lot, and I was so surprised by myself, because here, like, for example, a friend of mine has just changed the work, and he said, my boss. In my mind, he was a man. So like I said, oh, are you going to meet him tomorrow? And he was, no, actually it's a her. And I was, yeah, right, in a sense, but in the mind, immediately, boss is someone with a male. Why? In a sense that, again, it's a, as I always say, it's a cultural stuff. So
yeah. No, sorry, I just we were closing up, but I just clicked when she said professor.
But it was important. I mean, I do believe in this stuff. You know, this was the reason why I was calling you by your title. It is quite important, I think. So thank you again, everybody.
Thank you, and I hope to see you soon in person again. Yes. I really hope so.
Thank you.